Alrighty, so let's go over these here, guys. So for number 1, we've got dinitrogen trioxide. Ionic or molecular? Molecular. Alright, so we just use the prefixes to tell us how many of everything there is. Di means 2, so we're looking at N2, trioxide, O3. N2O3, 1 mark. Okay, calcium chloride. Calcium's a metal, so this one's ionic. Okay, Ca is +2, chlorine -1, drop and swap, and you've got CaCl2. 1 mark. All right, number 3. What does the little 2 next to copper tell us? Right, it's the 2+ charge copper, so that's the charge that we use when we swap and drop. Okay, and nitrogen is -3, so drop the 3 to here, drop the 2 to here, and you've got Cu3N2 as your formula. Okay, and number 4, magnesium sulfate. Okay, so magnesium is Mg, it's 2+. Sulfate is SO4 from your table of polyatomic ions. It is -2. Is that compound okay the way it is? Yes, it is. MgSO4. 1 mark. Questions on the first 4? All right. So for the last 4 here, we've got to give the names. So we've got sulfur and bromine together, ionic or molecular? Molecular, so we just write in the names with prefixes. We've got sulfur, okay, and tribromide. No capital letters. Okay. Number 6, we've got lithium and oxygen, ionic or molecular? Ionic, so we don't need any prefixes here. This is simply lithium oxide. Okay, number 7, iron and nitrogen, ionic compound. Anything special about it? Right, iron is multivalent, so we have to figure out which iron this is and put in the appropriate Roman numeral. Well, there's 1 nitrogen, and nitrogen is always -3. What's the charge on iron then? +3. So this is iron, 1, 2, 3, nitride. Okay, and number 8, we've got sodium and nitrates. Polyatomic ion and a metal, definitely ionic. So we've got sodium, and that's not a capital S. Sodium nitrate. Okay, so give them a mark out of 8. Guys, there's no half marks on any of these, so if you gave them some half marks, you got to take them away before you total it. Okay, give them a mark out of 8. Let them see it. Put it in the box, please. So this lesson, guys, lesson 1.1, isotopes, electron configurations, atomic structure, and the periodic table, is an AP only lesson. All right, so this is your first one that you will take that Science 10 kind of core does not take. All right, so this one is unique to you guys. If you printed out the regular Science 10 notes package, you won't have this one. If you printed out the AP one, you do. Okay, because there were 2 different packages. If you don't have it, it's not that big a deal. You can always print it tonight, okay, right off the website. I'll put the link in to the podcast like I always do. You can just follow it and you'll get there. So key points for today. We got to learn what isotopes are and why they're important, maybe some of their applications. Learn and understand the ideas of Bohr on the structure of the atom. Okay? Bohr, even though his model is, sort of not the most current model, he did find out a lot of really important stuff about how electrons can move about within the atom. Okay. Thirdly, follow the progression from Bohr's model to the quantum mechanical or electron cloud model of the atom. Okay, why we made that kind of jump. And fourthly, understand how the periodic table reflects these ideas. Okay, the periodic table isn't set up randomly. All right, the periodic table is set up actually quite brilliantly. All right, and the guy who made it, okay, Mendeleev, he actually built the periodic table before many of the atoms and elements that are on it were even discovered. He left spots blank on his original periodic table because he said, well, no one's discovered this yet, but it'll fit right there. Okay? He was actually able to predict the properties of some compounds that had not been discovered yet. Okay, so not compounds, elements, sorry, that had not been discovered yet. So the design of this reflects how many electrons you have in your outer shell, okay, the fact that certain physical and chemical properties repeat themselves periodically, hence the name periodic table, right? Things like that, right? So there's a reason why there's kind of a gap in the middle of it, right? It's because, well, there aren't any atoms in between here or elements in between here that show the properties that these elements down lower do, right? So there's a gap there to reflect all of that. Alrighty, questions so far? Good. So Dalton obviously said that all atoms of each element are identical, okay? And we know now that while that's essentially true, okay, that yes, they all have the same number of protons, okay, it isn't 100% true. Some atoms of an element may have more neutrons than others. All right, neutrons are kind of an odd thing, all right, and sometimes an atom may have more of them than the other atoms of the element do. All right, we call those special atoms isotopes. All right, they are typically the same generally in their properties. For example, when you look at, let's say, something made out of carbon, if you're looking at, let's say, like a lump of coal, all right, that's essentially pure carbon. When you look at it, can you tell that there are different parts of it that maybe aren't exactly the same? No, I mean, all of it looks like coal, but in that coal, okay, there are atoms of carbon that have more neutrons than other atoms of carbon, right? But to our, sort of the naked eye, and even, to microscopes and things like that, it's still essentially the same. Their behavior is the same. You'd never know. But we can use some of the properties of unique isotopes of carbon to do some pretty cool things, like carbon dating. How many people have heard of that? Okay, right? That actually uses a certain isotope of carbon that has more isotopes than the others, and the fact that it is somewhat radioactive, not enough to hurt you, obviously, right? But that it breaks down, and over time produces another thing, and you can actually see in an artifact, well, if this artifact was brand new, it would have this much carbon-14 in it. But it only has this much carbon-14 in it, so it must be this old. Right? And we use radiometric dating like that for essentially dating all fossils that we discover now. All right, so it's not entirely true. Some atoms of the same element have different numbers of neutrons. We call those isotopes. So these atoms are chemically alike because the number of particles that determine the properties is the protons. The protons are what determine your physical and chemical properties. Right? So really important that we understand that. That's probably something worth underlining, highlighting, okay? So the particles that determine chemical properties are protons and electrons, okay? That doesn't change in an isotope. They always have the same number of protons, okay? Always the same number of electrons. Just the number of neutrons that change. And the bigger an atom gets, typically the more neutrons it's going to have in it, okay? Above and beyond the number of protons. All right, so when you're looking at things like uranium and plutonium and things like that, they're very, very heavy because they have way more neutrons than they have protons and electrons, and so they end up being very big atoms. Okay. All right. Now, if you have an atom that has more neutrons in it than other versions of it, of the same atom, is it going to be heavier? What do you think? Yeah, okay. It would be like if you had a line of trucks, okay, and you loaded exactly the same number of bricks into all of them but one, okay, and into the last one you loaded 10 extra bricks. Is it heavier? Yeah, it's heavier by 10 extra bricks. Well, that's what an isotope is. It's a heavier version of the normal atom because it has more neutrons. Right? Some of the examples we have here, okay, this is the hydrogen atom. This is a normal hydrogen atom. Okay, this is deuterium. Okay? It is an isotope of the hydrogen atom that contains one proton, one electron, and a neutron. Okay? Most hydrogen atoms only have a proton and an electron, and that's it. Okay? Deuterium has a neutron in it. All right? This is the stuff that's actually used to cool nuclear reactors. CANDU, Canadian nuclear reactors. They are what we call heavy water reactors. They use water that uses deuterium oxide, all right, not hydrogen oxide. Everybody with me there? Okay. There's also a very rare isotope called tritium, which has 2 neutrons, 1 proton, and 1 electron. Okay. You're never going to be asked to recall those names. Okay, they're just an example. All right, which one of those would be heaviest? Tritium, yeah, okay. That'll be the heaviest one. Okay, so to show the differences in isotopes, we write the chemical symbol for that element with two different numbers to its left. Okay, the mass number, okay, is the superscript number. Okay, so the top one, this one here. Okay, and the atomic number is the subscript number. This is the number of what particle? Right, usually electrons, but always protons. Okay, because it's possible that lithium could get in a reaction and lose an electron and actually have one less than that. Agreed? Number of electrons can change if a chemical reaction occurs, but the number of protons, that can't change unless you do what to the atom? Split it. Okay, so 3 is the number of protons, which is why you see it in common for all of these isotopes. We said an isotope is different not because it has more protons, but because it has more neutrons. All right, so this is the normal lithium. All right, 6 and 3. All right, so this one here would be an isotope of lithium. Okay, 3 protons, but now has a mass of 7. Everybody follow me there? So how many neutrons does this have? 4. Right, and this one has 3. This one has 5. Okay, that's how we kind of figure it out. We take the atomic mass and we subtract the atomic number, and that will always tell us how many neutrons there are in an atom. Okay, and that's true for any atom on the periodic table. Right? If you look at your periodic table and you look at the atomic mass of hydrogen, it's 1.01, I think, on yours, right? Okay, something like that. So if you go 1.01 minus 1, what do you get? 0.01, essentially nothing. There's no neutron there, right? It's essentially telling you there are no neutrons in that atom. Right? But if you look at lithium here, okay, it's got an atomic mass of 6.941. If I go 6.941 minus 3, I get that there are how many neutrons? 4. Okay, we always round up. I get 3.964, that's 4. Okay, so the middle one, sorry, I messed up there. The middle one is actually the most common, okay, of the isotopes. Now, the atomic mass that you have on your periodic table is the average of all the isotopes of that particular element. All right, and it's not just an average of, we add them together and divide by how many isotopes there are. It's weighted. It's by percentage. So the vast number of, let's say for lithium here, for example, the vast number of lithium atoms are the variety that has how many? 4 neutrons. Okay, the vast number of lithium atoms that are out there have 4 neutrons. That's why, okay, the atomic mass is almost 7. All right, there is a small percentage that are 6, and there is a small percentage that are 8. Okay, very small, which is why the average is really close to 7. All right. Questions so far? Are we good with that? Okay. So the atomic mass of an element then reflects the weighted average. Okay, super important. Weighted average of all the isotopes of each element. So when we're looking at hydrogen, for example, its weighted average is 1.007. Are deuterium and tritium very common? No, they represent less than 1%. Okay, significantly less than 1% of all atoms of hydrogen. All right, because the weighted average for hydrogen is very close to exactly 1. All right, let's look at a different example here. Let's look at sulfur, for example. All right, here's the different isotopes of sulfur. Sulfur-32 has an atomic mass of 31.972, and it is responsible for 95% of all the sulfur that you would find. Okay, so it is by far the largest or most common isotope of sulfur. Okay. Sulfur-33 has 1 more neutron. Okay, and it has an atomic mass of 32.971. Okay, but makes up only 0.76% of all the atoms of sulfur that you would be able to discover. Right? So it's possible that if you could see 100 atoms, okay, of sulfur, you might not even see one of these. Right? It's less than 1%. All right, so it's possible that in a random sample of 100 atoms of sulfur, you might not even see one of these. Okay. Sulfur 34, okay, so it's got how many extra neutrons? Okay, has an atomic mass of 33.967, okay, and it makes up 4.2%. So it's obviously not as common, but it's quite a bit more common than sulfur 33. Okay, and finally, sulfur 36, okay, which has even more, right? Okay, it's got 4 more, okay, 35.967, but accounts for 0.014% of all the sulfur you might find. Okay, question? No, because we can't sit an atom in front of us and aim like a neutron gun at it and pick neutrons off, right? Like we can aim at a big, uranium atom and break it most of the time, right? But even in a nuclear reactor, there's a lot of misses, okay, on a big atom. So no, we can't just pick one off yet. We can create isotopes by doing nuclear fission, but we can't make specific ones, right? Yeah. Alrighty, so does that make sense there, guys? So when I find the actual atomic mass of sulfur, okay, the actual atomic mass of sulfur is 32.066, right? That's the weighted average of all of these. So what we do, okay, is we take the atomic masses and we multiply by the percentage that they occur in nature in. All right, so we take, for example, sulfur 32, and we go 31.972 times 95%, 0.95. Okay, add that to, okay, 32.97 times 0.0076, okay, and so on and so on. That gives us the average, more common atomic mass for sulfur. Okay, so it takes all the different varieties in. Now, we've done these kind of studies for essentially every atom, every element on the periodic table. This is what helps us do the radiometric dating stuff, like the carbon dating. Okay? If we know that, let's say in carbon, that carbon-14 comprises, let's say, 5% of all the carbon in a material. If we're looking at a material and we find that it has less than 5% carbon-14, is that stuff old? Yeah, because the carbon-14 is broken down into other materials, right? There's less of it than there should be. Everybody follow? Okay, when something's new, it has this percentage of carbon-14, but as it ages, the carbon-14 breaks down, turns into other things, and there's less and less and less of it. All right, so there's two ways to go about it. Look for the amount of carbon-14, or look for the amounts of things that it turns into. All right, questions there? Okay. Again, this is probably not something I'm going to ask you to do. All right, it's just so you understand sort of how it works. All right, the boring world of Niels Bohr. Okay, so 1913, Bohr proposed that electrons were arranged in concentric circular paths or orbits around the nucleus. It made sense. Planets orbited the sun. This eliminated the possibility that electrons run into each other, although I don't know why that would be a problem. Okay, it just was easy to visualize, easy to organize. Okay, so Bohr answered in a novel way why electrons are attached. Why electrons which are attached to protons never crash into the nucleus. Right? I mean, I shouldn't say attached, it's attracted. I read it wrong. Felt a little dyslexic there. Okay. So if electrons are attracted to protons, shouldn't they move together? Okay. What keeps them apart? Okay. The neutron partially in there. Okay. But there's also, I mean, the Earth is attracted to the sun. Thankfully, we don't crash into it. Why? Yep. We're stuck in orbit. And why are we orbiting? Right. Okay. It's as simple as this. This is what happens when you make budget cuts to education. You get ghetto physics. Okay. All right. So this thing's whirling around and around and around in a circle. Am I always pulling it towards the center? Yeah. If I wasn't, it would fly off in a circle. If I let go of the string, I'm no longer pulling it towards the middle, and it'll fly off in a straight line. All right. If it moves fast enough, it stays in this circle. If it doesn't move fast enough, it moves in, right? It moves towards the center. I mean, because gravity's here, it pulls down. But okay, if it slows down, it actually moves in towards the center. All right. So these electrons have to have enough energy that they keep moving and that they stay a certain distance away. If they gain more energy, they'll move farther away. Okay? We talked about that the first day, right? We talked about how in some things like that glow-in-the-dark material, electrons get excited and they move faster and they move further away. Okay? All right, so he proposed that electrons in a particular path have fixed energy, which we still know to be essentially true. Okay? Thus, they do not lose energy and crash into the nucleus. The energy level of an electron is the region around the nucleus where it's likely to be. Can we pinpoint exactly where an electron is? No, but we know where you are likely to find it based on its energy. Okay? That place is called an orbital. Okay? The place where you are likely to find an electron is called an orbital. Okay? This is the simplified way to look at electron orbitals. They are actually not at all this shape. All right? Right? We still know that, however, this arrangement in terms of the number of electrons in an area is essentially still true. Okay? The first electron level, lowest energy, has 2 electrons in it. It's going to only hold 2 because there's only so much room. It's a small circle. Okay? The next one out can hold 8 electrons. The third one out can hold 8 electrons. When you get further out, most of the time it's 8. Sometimes it gets to be 16 or 32, but we don't deal with any of those. All right? Questions on that one? Okay. So these energy levels are like the rungs on a ladder. Okay? Do you have to put in energy to climb a ladder? Okay, so the farther away from the bottom, or in this case the nucleus of the atom, the more energy the electrons have to have. All right? The opposite's true if it loses energy. If you put your feet on the outside of the ladder and let go, you do what? You slide down the ladder, right? Okay? Do you pick up speed? Yes. Okay? Is that essentially losing energy? Well, sort of. You won't let yourself pick up that much speed because you'll get hurt when you get to the bottom. So what do? You squeeze your feet against the ladder. Right? Does that create heat, and does that represent a loss of energy? It does. Okay? And so that's what happens. As electrons come back down, they lose energy, they give it off, okay, whatever. All right, so electron can only be found on a path, but not between them. So what happens is if an electron gains energy, but it's not enough to move out to the next one, it stays here. It moves faster. It isn't until it reaches a certain energy level where it will make the jump. All right, we call that jump a quantum leap. All right, it is making a leap from one quanta or energy level to the next. So it is a quantum leap. All right. Okay, and in the same way, using this ladder analogy, you can't stand here. Okay, because there's no rung on the ladder there. There's nowhere for the electron to be. That's a place where, okay, there's simply not a place to stand. Right? You can't stand in between the rungs of a ladder. It would be a neat trick, but you can't do it. Okay. Okay, so the amount of energy gained or lost by every electron is not always the same. Okay, so this is where the ladder analogy breaks down. The electron levels, okay, the energy levels, the orbitals, are not evenly spaced. So it would be like climbing a ladder where all the rungs are a different distance apart. Okay, the further out you want to go, the more energy it's going to take to do that. All right, so it kind of gets exponentially, well, not so much exponentially, but it requires more energy each level up you want to go. It's not an even thing. Okay, so a quantum, okay, a quantum of energy is the amount of energy needed to move an electron from its present energy level to the next highest one. That is, to make a quantum leap. John, can I maybe just flip off that front bank of lights so we can see this diagram a little better? Next switch. There you go. Okay, so in this picture here, okay, it's just like a sort of a computer-generated model. It's not a picture of an atom, but it gives you some idea of what those energy levels might look like and what electrons would look like as they move between them, okay, and in them. So really close to the atom would be that low energy level. Okay, and then there'd be, these orbitals here that are in green, okay, that are available to slightly higher energy electrons. Right? Is that quite a distance from here to there? Yeah, okay, and you can see that, you know, they can move about sort of within that orbital. Okay, there's also these orbitals out here, right, that are even higher energy. Okay, and then there's these odd ones, okay, that are right here and here, right, that would be even a higher level of energy above that, right? When you get into them, okay, you move around with a very high rate of energy. Now, what do you notice about the brightness level of these as you get further away? It gets dimmer, right? That represents the fact that fewer and fewer electrons are actually able to acquire the energy to get to those levels. More often than not, the inner levels are full, right? An electron has to have its inner levels full before it can fill the outer levels. Okay, everybody good with that? Right. Okay, so the quantum mechanical model, we also call it the Electron Cloud model, okay, leads to this quantized idea, okay, that electrons have a certain level of energy, they're quantized, they go up to the next one, okay, they have more energy, right? So it does not define an exact path, okay? It doesn't say that, like Bohr's model, this energy level is a circle that has this radius, this energy level is a circle that has this radius. Orbitals are not circles, okay, at least not all of them, all right? Sure, the one closest to the nucleus is probably a circle, but beyond that, they take on odd shapes. Okay, and this is kind of like what you saw in that last picture. You can see these, okay, strange shapes where an electron would be. Now, why don't they move in a circle? Well, all electrons are what charge? Negative. What are they going to do to each other if they get close? They're going to repel each other. So as they fill up these energy levels, they might move around, but then they'll get close to electrons in the other orbitals, and they'll repel each other. So they kind of stay put. Right? They create for themselves kind of a personal space. Okay? And they kind of stay in there because they're repulsed by the others. Okay? All right. So the electron cloud is dense where the electron is likely to be, and obviously less dense. And you can see on this last diagram, there were areas where it was not very dense. Okay, in here, yeah, there's lots of electrons. They're more likely to be in here. It's closer. Okay, as you get further out, okay, there's less and less of them. All right. Questions so far? All right. So in the quantum mechanical model, the energy levels of electrons are designated by principal quantum numbers that you will never be asked to remember until Chem 20. Okay, and in Chem 20, then you have to do this whole, the electron arrangement of this is 1s, 2p, 3d. You don't have to do that in Science 10. Okay, Mr. Real does a way better job than me, okay, of explaining this stuff. All right, so each energy level is divided into sub-levels, and they all have different shapes. All right, so this here, this circle, would be the first and lowest energy level. All right, the one that's closest to the nucleus. All right, the next energy level from there has this shape. Okay, essentially a circle, maybe squashed a little bit, but arranged vertically. So it kind of sits on top of this one. Okay, if you can imagine that, that would be the next energy level. Okay, and then these two here would be the next ones, and they would be arranged like this. Everybody with me there? Each one of those orbitals can hold 2 electrons. Okay, so each one of these circles can hold 2 electrons. All right, as we get more electrons, well, we have to have more levels. So we start getting these kind of really weird shapes. All right, we start getting like these teardrop ones that go on top, like this. All right, and then you got this circular one, okay, that kind of goes almost in between these other ones. It starts to get really crazy to draw. Okay, kind of like this. Okay, more around that. Okay, and then you've got these ones here because it's 3-dimensional. That's the problem. I can't draw 3-dimensional. Okay, so now these start to fill in the spaces in between these 4, and so on and so on. As you get more and more electrons, you start squishing, okay, these other orbitals into the open available spaces. But obviously, you filled close to the nucleus. You're always getting a little bit further away. Okay, everybody with me there? Again, you're never going to be asked to draw this. You're never going to be asked to label the numbers. Okay? It's just important you understand that electrons have certain spaces they're supposed to go, and that's based on the energy they possess. If you have a high energy electron that's losing energy, okay, it starts to move closer. But it can only move closer if there's an orbital available. All right? So typically you don't see one push another one out because it would require energy to do that. That electron has already lost energy and is moving back. So typically you don't see them bump each other out of the way. Yeah. I mean, this keeps going until you've got enough orbitals for everything, but it starts to get wonky, all right? When we get into like the transition metals, the things that have more than one possible charge, they fill their orbitals in a strange way, okay? And when you get to the actinides and lanthanides, then they get really, really crazy, okay? This is just for the representative elements, the ones that just obey all the rules and are nice, okay? Yeah. All right, so the principle of the quantum number, okay, principal quantum number always equals the number of energy sublevels. This is the thing you don't even need to know, okay? So here's our first energy level, okay? We can hold 2 electrons in there, so if it has 1 electron in the first level, it's 1s. If it has 2 electrons, it's 2s, okay? And then we start filling up, right, these other ones. And this way, you can see better in 3 dimensions how this looks, all right? There's your first one, okay, x, y, and z. So here's the one that's on the y, or in the plane of the y. Here's the one that's in the plane of the x. Here's the one that's in the plane of the z, all right? And so they can offset because it's 3 dimensions, right? So you got this, and then you got another one that goes diagonal to that in the 3rd dimension, right? And so there is space there, but it gets pretty cramped. Okay, maybe this diagram's even a little better. Okay, so 1s, then 2s. Now that first one is full. Okay, then we can start filling up the p orbitals. Okay, and then we can start filling them up. You get to the d orbitals. Okay, and so on and so on. You don't typically fill these until the lower ones are filled up themselves. All right, so a couple of things to remember here. Okay, there's rules that dictate how the electrons fill the orbitals. All right, I might ask you about these 3 rules. That would be about the only thing I'd ask you from this lesson. Okay, so the rules are this. The Aufbau Principle says that electrons enter orbitals lowest energy first. It's like when you go to the mall. If you're the first one there, you park close because the spots are available. But if you get there last, you're out on the periphery and you have to walk half a kilometer across the parking lot to get to the door. Right? Works a lot like that. All right. The Pault exclusion principle. An orbital can only hold 2 electrons. Okay? That's all you need to remember about that one. Okay? And then Hund's rule. Hund's rule is essentially sometimes called the repulsion principle. Okay, electrons go into this orbital 1 first. Okay, then it'll fill the next orbital before any pairing occurs. Right? They don't want to get stuck in an orbital with another electron if they can avoid it. So they start filling them 1 at a time. When they're all full, then they'll start pairing up. Okay, so electrons occupy orbitals. 1 electron enters each orbital of an energy level before any pairing occurs. Okay. Okay, just gonna kind of insert something here and show you what I mean by that. We've got to picture this. It's easier to picture this from Bohr's perspective. All right. So here's the nucleus of the atom, where the protons and the neutrons are. All right. Hydrogen, one electron. Okay. That orbital is now half full. All right. Then the next time for the next atom up, helium, the electron goes as far away from that one as possible in that orbital. Now that orbital is full. All right. Next orbital can hold how many? 8. But they'll fill it like this. All right. There are places where those can go. If you recall, okay, the next orbital looked like 4 of the kind of squashed circles, 4 ovals, right? Well, these are the places where electrons can go, those 4 squashed ovals. All right. When a 5th electron has to come in, it'll pair up with one that's in one of those squashed ovals, and then it'll pair up with this one, then with this one, then with this one. All right? They do it like that. They fill each orbital Okay, one in it first, and then they start pairing up. No, I'm just, yeah, it's random. Whichever one, because like I say, we recognize it as this shape, but it's not a rigid shape, right? These shapes can change based on other atoms being nearby and whatever. Okay. So here's your periodic table. Okay, obviously you've seen that before, but what we need to recognize is the beauty of its organization. Okay, everything in the first column here, okay, shares similar physical and chemical properties. All right, the first column is often known as the alkali the alkali metals. Okay, they are highly reactive with water. All right. Has anyone ever seen what happens when you throw sodium into water? Okay, sodium is actually quite docile compared to some of the other ones. Okay, if you throw like rubidium or cesium into water, you get a much more vigorous reaction. Okay, if you go one over, you've got what are called the alkali earth metals. All have very similar properties. They're relatively reactive. Okay, they're kind of soft, silvery metals. Okay, so are the ones here, right? And they do a lot of the same things. You got your transition metals in here, all right? And again, they show some similar properties, right? But even more so when you get over here. If you get to the halogens, okay, fluorine, chlorine, bromine, iodine, and astatine, they all have very similar properties. Okay, and then your noble gases here. Noble gases don't participate in chemical reactions. Right? They're unreactive. Right? Their outer shells are full. They have absolutely no reason to join up with anybody. They're happy the way they are. Okay? All right. So, like we said, modern periodic tables set up to reflect chemical and physical properties, electron configurations, okay, and atomic structure. And Mendeleev was the guy who put that together. That could be a multiple choice question. Okay. Who was responsible for putting the periodic table together? Dalton, Thomson, Mendeleev, Bohr. Right? And he's the one who realized that properties occur periodically, okay, or at regular intervals of electron configuration. All right. Now, if you look at the periodic table here, when Mendeleev put this together, all right, like we said before, a lot of these weren't even discovered yet. Okay, people didn't know about. I think it was this one wasn't there. Germanium wasn't there. Gallium might not have been there. This one was man-made, so it wasn't there. Okay, things like that. So he had gaps in the periodic table, right, when he made it. But he knew something would fit there. He just didn't have any materials that had the properties these other ones he knew about had, right? So he knew manganese had certain properties. Well, we should probably use representative ones here. He knew magnesium had certain properties, strontium had certain properties, barium had certain properties. So he had been able to guess what his missing ones were. Obviously, calcium wasn't a missing one. He knew about it, but okay, you get the idea. He was able to predict the properties of the atoms and elements before they were even discovered. Okay, so terminology to do with the periodic table. Okay, a family or a group is a column on the table. All right, so group 1A, okay, is the first column. So that's hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Okay, group 1A. Group 2A, okay, 3A, all right, and then you go over and they kind of go along like that. All right. A period is a horizontal row of elements, okay, along the periodic table. Okay, so you got groups that are vertical, periods are that are horizontal, and we always see a progression, okay, of properties. We go from highly reactive, less reactive, okay, until we get over to here again, where as we get towards the end, you see the electron shell filling up and certain properties occurring again, and you see that happen in each row on the periodic table as we go along. Okay, we see the shells filling up, okay, and certain properties showing themselves again on a sort of regular pattern. Okay, we already talked about this one here, metals on the left and nonmetals on the right. Okay, periodic tables list properties of each element in their boxes. Okay, a key is usually somewhere on the table. So if you look at your periodic table, what's that? Yep. Whoa. All right, so here's the key on yours. All right, you can see that, like we said, it's iron, and it shows the atomic number, right, which is the number of protons. Okay, it shows the electronegativity, which is a number that describes how hard it holds onto electrons. Okay, it shows the symbol and the name, and then up top here we got the atomic mass and the most stable ion charges. All right, so that's the information you can get from this particular periodic table. Some periodic tables show different information. It all depends on what you want. Typically, but again, there's such a low percentage as to essentially be non-existent. Yeah. Something else to remember about these charges, guys, is the one listed first is the most common. All right, so the one listed to the left is the most common charge of that ion. All right, so looking at the groups here, all right, the noble gases, okay, elements that have the outermost S and P sublevels full. Their outer shell is full. Right? Those elements are sometimes called the inert gases because they rarely react with other substances. Right? You just don't ever see a compound that's like, let's say potassium neonide. Okay, like you don't ever see it. Neon doesn't react with anything. Okay, argon doesn't react with anything. Krypton and so on. Right? These are typically also used in light bulbs. Okay, fluorescent type light bulbs. Especially now, if you look on some cars, have those really bright headlights. They're called HID or bi-xenon headlights. Because what do they use in them? Xenon gas. Okay, they run an arc of electricity through the xenon gas. The electrons get excited and glow. Okay, and that's why you get the really bright lights. All right, halogen lamps. What do you suppose they use? Halogen gases, a little less bright. Okay. All right, representative elements. Okay, representative elements. Okay, outermost S and P sublevels are only partially full. If they're only partially full, that means they can either lose or gain electrons to get a full shell. So these are the ones that behave in a predictable fashion. All right. Yeah. So representative elements. Okay, group 1A, 2A. Okay, and then over here 3, 4, 5, and so on. You get these A group elements. It doesn't even show it on your periodic table because it's not something that's ever used. Okay, transition metals, outermost S sublevel and nearby D level contain electrons, often called the group B elements. That's all of these ones here in the middle that have that have more than one possible charge, behave kind of oddly or less predictably, right, and that kind of thing. Okay, inner transition metals, okay, are your lanthanides and actinides. They're the ones that appear on these lower levels that are kind of chopped out of the periodic table, right? And the only reason they do that is because this row here, okay, and the row below it would be way too long to fit. Everybody follow me there? Okay, so all of these essentially in the lanthanide and actinide series behave exactly the same. So they're chopped out and put down below. Right? They still follow that same pattern. They fit underneath the rows that they apply to. Okay. Okay, alkali and alkali earth metals. So elements in group 1A are the alkali metals. Okay, this is what typically your alkali metals look like: soft, silvery black, they oxidize quickly. Okay, they have low densities, low melting points, good electrical conductivity, soft enough to be cut with a knife, okay, and rapidly oxidize in air or water to produce highly alkaline solutions. That means highly basic. Right? If you throw sodium in water, when the reaction is done, you have sodium hydroxide. Right, the stuff that's in oven cleaner. You have a solution of sodium hydroxide sitting there. Very basic. Okay. And then in group 2A are the alkali earth metals. They're harder, okay, but they're not as violently reactive. They're still fairly reactive and they oxidize quickly, but they don't explode when you put them in water. Okay. In fact, the alkali metals, okay, the first group, are so reactive that if we have them, they actually come in a container where they are submerged in kerosene. Right? They submerge them in kerosene because then they can't come into contact with water in any way. Sodium will start to react with the water vapor in the air. Right? It is that reactive that you don't even have to throw it in water to make it react. It'll react with the water vapor in the air. All right? And you see that with lots of sodium-containing compounds. If you have pellets of sodium hydroxide sitting out, they start to get molten. They just start to get gooey because they're reacting and quickly absorbing water right out of the air. Okay. All right, the halogens, okay, elements in group 8A are the halogens, or 7A are the halogens. They are not found in their free state in nature. Okay, you never just see chlorine gas, okay, or iodine or anything like that in nature all by itself. They're always, because they're so reactive, in a salt with something else, okay, as an ionic compound. Okay, so give you an idea here. This tube here, I believe, is fluorine. Okay, the tube that's got the green hint to it is chlorine. This is bromine, and then iodine. All right, so iodine is the only halogen that's actually a solid. Okay, comes as is a solid. Astatine is a solid as well. Okay, bromine is a liquid. Right, the other two are gases, fluorine and chloride. Okay, chlorine. What happens to it if you inhale it? Yeah, okay, it will react again with the substances in your lungs, and it creates a highly acidic solution, right? And it can destroy your lungs. Okay, that's what happened to the Canadians who were fighting at Vimy Ridge. Okay, the Germans gassed them with chlorine gas. They would actually, the survivors often describe these green clouds that would float over the trenches. Okay, and then if they inhaled it, their lungs just, right, and that was the end of it. Right. Only thing that saved some of them was a urine-soaked handkerchief over their face. Okay, because it would react with the moisture and the urea and stuff in the urine in the handkerchief and be caught essentially in the handkerchief and not get into their lungs. Yeah. I think you'd have to be pretty desperate to pee on a cloth and put it on your face, but okay, such is the way things went then. All right, so that's all we need to know about all the electron configuration stuff. Okay.